Bismillahirrahmanirrahim. Assalamu alaikum ji. We'll continue our discussion on neural networks. Building on our knowledge about perceptron and logistic regression, we gave you an overview of neural networks in the previous video. Here we'll focus on the notation for neural networks. How do we define input? How do we define output? And how do we relate these two given the parameters of neural networks? And we'll also talk about the forward pass, that is traversing neural network from input to output. And what are the equations we should use for this traversing or for the computation of output given input and given the parameters of neural network. Right? We start with single neuron, and let's revisit the notation we adopted for single neuron. That's how we define the output of single neuron. We have activation function. Input as a linear combination of the inputs, right? So a weighted combination of inputs plus bias. Right? If I use a variable z to denote this linear combination, right? So z is W transpose X plus B, and we call this as pre-activation output of a neuron. And we pass this pre-activation output of a neuron through an activation function G. So from now onwards, I will refer to Z as, I will use Z to denote to pre-activation output of a neuron, and we pass this Z to through an activation function G to obtain the final output of neuron. So this is the output for one input. If we have a number of training data points, let's say we have n data points, and if we stack all of these n data points in the form of matrix, right? So a matrix X in which we have stacked all the n inputs, where each one input is of size D, number of features is D. And if I construct a matrix X in this form by simply stacking all the inputs, the size of X would be D cross N. And now I'm going to define the output when we have all the inputs are present, or what is the formulation if we have all the inputs for the output. So I will be using this X, and by defining 1 as a row vector of ones. So 1 is a row vector that contains ones, and the length is n. Right? So for one input, we had W transpose X plus B. If we have n number of inputs stacked in a matrix X, Z would be W transpose capital X plus B1. So what is Z? So Z is a vector containing Z1, Z2, Z3, Z4, and Zn. So Z1 is the output, is the pre-activation output for input X1. And I can compactly represent this Z in this form. This is the pre-activation output, or we can say this is a linear transformation of the inputs. And if you see the consistency of this matrix multiplication, matrix vector multiplications, so we define B as a row vector of length n. So B is 1 time n, 1 cross n. X is D cross n. W, the weights. How many weights? D. So 1 cross D, and consequently we have 1 time 1 cross n as dimension of Z. Right? And if we pass this Z through activation function, activation function is defined for a scalar. But if I say if I pass a vector and we define operation of activation function on a vector as it is acting on each quantity or each term of the vector. So using the activation function, we obtain A, which is G of C. This is activation, or this is, as we said earlier, this is nonlinear transformation of Z. So activation function is operating on each entry of Z. So A is a row vector of length n, and obviously using the notation what we have, ith entry represents an ith output. Represents an output for ith input. So I hope this is clear, right? So the summary is we have Z is equal to W transpose X plus B, pre-activation output for one input, and you pass through G of Z, you get output for one input. We can compactly write for n number of inputs in this form for pre-activation output, and we pass this Z through activation function. We obtain A is equal to G of Z. Right? So we will revisit this notation when we define forward pass for all the inputs. Right? For now, we're going to define the notation for neural networks. So we usually use capital L to denote number of layers of neural network. If you have seen previous video, we note that we do not count input layer in the number of layers. So number of layers include the number of hidden layers plus the output layer, plus one. So number of nodes in the nth layer, we use small m superscript in square brackets, this L. So this square bracket indicates that we are referring to the nth layer. Similarly, we use a subscript I superscript L in square brackets. It means we are referring to some quantity that is associated with nth layer. So AI denotes the output of ith node of nth layer. And if I concatenate all of these inputs in the vector form, I can define a vector A, a vector of outputs of nth node. What is size of A? What's the length of A? Number of nodes in the nth layer, right? So size of A would be AL, size of AL would be M subscript L. So for input layer, A0 is equal to X, which is input layer. And finally, AL is, because total number of layers is L, so AL corresponds to Y, or output of the output layer. Okay, let me illustrate this with the help of one example. This is what we have seen earlier, a 3-layer network, 2 hidden layers, L is equal to 3. Right? And if you have this network, for this network, the number of neurons in the first hidden layer is 4. So M superscript 1 is 4, M superscript 2 is 3, and M superscript 3 is 1. Number of neurons in the third layer, output layer, number of neurons in the second hidden layer, number of neurons in the first hidden layer. Right? So A subscript 2 superscript 1, this is the output of the second neuron in the first layer, in the first hidden layer, right? Okay, let's continue defining notation. So we have defined inputs and outputs of each layer, right? But we also need to define the weights and bias, which are the parameters of each neuron. Right? So I will be using W subscript I superscript L. The weights that are associated with ith node in the ith layer. Similarly, BIL is the bias for ith node in the ith layer. If I further zoom into this vector W, so the jth entry of this vector WIL would be WI comma JL. This denotes the weight and bias associated with the jth input of the ith node in the ith layer respectively. And this all will make sense. Let me say we have this, right? So what about if I ask you, where is W1, 1, comma 2? So the superscript indicates first layer. The first subscript indicates first node. Second subscript indicates the input layer, right? So W12 is the weight, which is for this input coming. Right? I hope this is clear. If I ask you, using the notation, can you relate the output of the first hidden layer? What about the output of the first neuron in the first layer? Let's say we want to determine the layer 1 output. What about the output of the first neuron? Pre-activation output would be W11 transpose X plus V1. Right. So weight for first neuron, first layer, bias first neuron, first layer, and we get Z11 pre-activation output. And we pass this pre-activation output through an activation function, and we obtain A11. Okay. And if we build on the same notation, we can obtain the output for other 3 neurons in the layer 1. Right. So these are the 4 equations representing the outputs, set of equations representing output for the first layer. Right? Okay, let's combine all of these and have a compact representation. So we have this layer 1 output. If I define a matrix W, which is W, I stack this weight vector, the vector for the second node first layer, a vector for third node first layer, a weight vector for the fourth node first layer, and stack all of these weight vectors in this matrix form W. And they call it a matrix W superscript 1. It means it has the weights for all the nodes in layer 1. And I define a vector B that has the bias terms for all the nodes in layer 1. Right? The first entry, the bias for the first node in layer 1, second entry, the bias for second node in layer 1, and so on and so forth. And also define, if I also stack all of the pre-activation outputs in a vector Z. Can you help me in writing all of these 4 pre-activation outputs in using one equation using the notation defined here. Yeah, this is super simple, right? So you see x is common, x is same, input is same for in each of these equations, right? So we can compactly represent this in this form. So z would be w1 x plus b1, and we know that x is a0, right? So we also use a0 to denote x, right? So because this is the zeroth layer, input layer is the zeroth layer. So once we have z in vector form, we pass this z through an activation function to obtain the activation output, the output at this stage, right? So this is a, right? So a is a vector that has 4 entries, a11, a21, a31, and a41, and so forth. So now we have a single equation relating input to the layer and output to the layer. And in this equation, W and B, so W is a matrix that has all the weights associated with all the nodes in that layer. And B is a vector containing bias terms. So W1 and B1 are the parameters of the first layer. Right? Let's build on this. So this is what we have defined, relating input to the first layer and output to the first layer. If I ask you, what's the size of W? What size of X? 3, right? So number of columns in W should be 3. What about the number of rows of W? Number of nodes or number of outputs in the first layer? We can say the answer is number of nodes times number of inputs. In this case, for this example, this is 4 times 3. 4 outputs, 3 inputs in layer 1. Or we can say this is equivalent to number of nodes times number of nodes in the previous layer. We're generalizing it, right? Okay. Can we write output of second layer using the notation we have defined? Can we relate input to the second layer to the output of second layer? What is input to the second layer? A1. Output of first layer, right? And what about the output of second layer? A2. How do we relate? Simply using a matrix W2 and B2. And that's it. For this layer, so we have this. And these two equations defining or relating output to input. So A1 as input, weighted combination plus bias, you obtain pre-activation output, you pass it through activation function to obtain the final output of the second layer. Similarly, we can have for the third layer. I assume you are now trained. What's the size of W2? Number of nodes times number of nodes in the previous layer. It should be 3 times 4. What is the size of W3? 1 times 3. Right? And finally, we note that the WL and BL denote the parameters of, contain the parameters of the LF layer. So using these 3 equations, right? So using this one, and this one, using these equations, we can determine the output given input and parameters of layers. Right? So we sequentially traverse the network. We first obtain A1 using X, and then compute A2 using A1, and then compute A3 using A2, and so on and so forth. We're traversing network. And this traversing is what we already know is forward pass, right? And this is all consistent mathematically in terms of size of these matrices. So this is the forward pass summary for this example. We can generalize it. Right? So in general, we can say output of lth layer, so Z, pre-activation output of lth layer is weight matrix for that layer times output of the previous layer, L minus 1 layer, plus the bias of the lth layer. Right? So we can say in general we have ZL is WL AL minus 1 plus BL, because AL minus 1 is output of the L minus 1th layer, and that is acting as an input to the lth layer. And once we have pre-activation output, we can pass through activation function to obtain the final output of the layer. And we have such equations for each of the layers L. For L is equal to 1, 2, and 2 capital L, total number of layers we have. And we know that A0 is 0th layer, output as your input. A0 is X. By the way, if we ask you for this example, how many parameters do we have? So what about number of parameters in the first layer? We have 4 nodes, 3 inputs, right? 3 weights for each node. So in total we have 12 weights plus 4 bias terms. So we have 16 parameters for this. We have 4 inputs, 3 nodes, 4 times 3 is 12, plus 3 biases, 15 parameters for this node. And here we have 3 inputs, so 3 weights plus, and we only have 1 node, 3 plus 1, 1 bias term is 4. Right? So in total we have 35 parameters. Right? So this formulation, what we have here is for one input X. How can we extend this formulation for a stack of inputs or a bunch of inputs, say for n inputs? Okay, let's build this. So we know that this is for the first layer, and if you recall, when we define this neuron earlier in the video, we said this is the output for single input. And if we stack all the inputs in a matrix capital X, we obtain this formulation for n number of inputs, right? So where A is a row vector of length n, and ith entry of A represents an output for ith input. So what's up here is 2 equations relating input and output for the first layer for single input. If I combine these two, so I can simply replace X with capital X, right? Because when I moved from here to here, simply replace X with capital X, and obviously we introduce this vector of 1s. Similarly, we can define a matrix Z1. So when Z is a vector that has output, pre-activation output for one input, but all the nodes. But now Z is a matrix, right? So one vector of Z, the first vector of Z, the first column of Z represents output for all the nodes for the first input. Second column, output of all the nodes for second input, and so on and so forth. Okay. Obviously, the B is also a matrix here, right? Although to be consistent with the notation, I have used small letter to denote B, but B is a matrix. Sorry. And once we have this Z, we can see this is mathematically consistent. Size of W, 4 times 3. Now X is 3 inputs, but you have n number of inputs, sorry, 3 features. Size of X is 3, but we have n number of inputs, so 3 times n. What is B? 4 times n. So how do we relate these two B's? Right, this is important, right? Let me explain. Right? So up here, B is a vector. Right? What is the size of B? Number of nodes in the layer. So it's the number of rows is number of nodes, and number of column is 1. So B is a column vector. And if I concatenate, right, the same B n times, if I stack this the same B n times, right, I get this 4 times n. This matrix is having the copies of B, n copies of the vector up here. And finally, we obtain 4 times n. So Z is a matrix containing output for the first layer for all the inputs, right? And once we have Z, we pass Z through activation function to obtain A. And again, let me iterate here. Let me reiterate that G is acting on each entry of the matrix because G is defined for scalar input, right? Okay, this is the output relating. These are the equations relating input and output for layer 1. We can build on this and we can define equations for the layer 2 and again for layer 3. And you can quickly see that these are all mathematically consistent. Finally, you obtain n number of outputs for n number of inputs. So these are the equations for this network, this example. In general, we can say, so ZL would be WL capital A L minus 1 plus BL. And if I write this, this is what we have for equation for any layer. So that is relating pre-activation output with the input AL minus 1. So ZL pre-activation output, L minus 1 input to the layer. And we can relate, we can pass the ZL through activation function to obtain the output of the LF layer. And we have these equations for every layer 1, 2, 3, up to L. Right? So we have defined a 2 set of equations. So for forward pass, and 1 set of equations representing 1 input output when we traverse the network for 1 input, in which X is a vector. Output of every node is a vector. And in this formulation, in this slide, we have the formulation for when we have stacked all the inputs in the matrix, and we can use these equations to obtain all the outputs by following these equations by traversing the network from input to output. Right? So that was about forward pass and the notation we have used for neural networks. In the next video, we will talk about the activation functions we can use for neural networks, or what are the possible choices of activation functions we have in the literature. Obviously, we cannot cover all the activation functions, but I will review pros and cons of the most commonly used activation functions. Right. So we stop here and we'll continue in the next video, inshallah. Allah Hafiz.